In kinematics of 2 dimensions, that is the description of motion in 2 dimensions, the circular motion is an application to such motion. When we work in circular motion, it's better to use the polar coordinates rather than Cartesian coordinates. That is, using the variables r and theta instead of x and y. However, the circular acceleration, the circular motion, is divided into 2 types. One is called uniform circular motion, where we have a centripetal acceleration only. And obviously, this centripetal acceleration is attributed to the change in the velocity vector while the object is moving in a circle. And the change in the velocity vector is due to the change in the direction of this vector, while the magnitude of the velocity vector is constant all the way during the motion. So now, again, in this motion, we have a constant speed, that is constant magnitude of velocity, while the direction is changing. Again, the change in the direction will make the velocity vector changes, and the change in the velocity vector will cause to an acceleration. The question you may ask, what causes this kind of motion to be uniform, and what causes this object to move and change its direction while keeping the magnitude of the velocity constant? The answer is a centripetal force. That is the force acting perpendicular to the direction of the velocity and towards the center. And this centripetal force will give us the centripetal acceleration. Now, the second kind of motion, of circular motion, is the non-uniform circular motion. In this motion, the difference in here, we will have the magnitude of the velocity changing in addition to the change in the direction. So we're going to have both the magnitude and direction of the acceleration changes. Now again, the change in the direction will give us the centripetal acceleration, while the change in the speed or the magnitude of the velocity will give us additional acceleration that is tangent to the circle, and we call it a sub t. And a sub t actually is caused by a centripetal by tangential forces. So the tangential force that causes, or that give us the tangential acceleration, and the centripetal force that gives us the centripetal acceleration. So the resultant acceleration here, and these two accelerations, as you see, perpendicular to each other because the tangent is perpendicular to the radius, and here AT is perpendicular to AR, and we can get the resultant acceleration in this case. And we may call it non-uniform because the velocity vector, the magnitude of the velocity vector changes from time to time, as you can see in this figure. Here, a mass attached to a string is rotated in a uniform circular motion as shown in the horizontal circle. As we said before, the speed of the object moving in the circle is constant. That means the magnitude of the velocity is the same wherever the object is in its circular motion. However, the direction of the velocity as shown is changing, and this means that the velocity vector changes, and the change in the velocity vector will cause a change in the acceleration, and that acceleration is going to be the centripetal acceleration. What causes this motion is a net centripetal force, and this net centripetal force in this case is the tension in the rope. It's the only centripetal force acting on the object as it is attached to the object. The minus sign shown in the formula indicates that the direction of the acceleration is towards the center. This is because every particle is drawn from the center outward in this direction. Every r vector has a positive sign in polar coordinates when it's drawn from the center outwards. That's why the acceleration takes this negative sign, because it is opposite to this positive vector r. However, as shown in the formula, v and r are both constant in such motion. In this uniform motion, you might ask, how did you get this answer of v squared over r for the centripetal acceleration? Well, to do that, to prove that this centripetal acceleration is v squared over r, we simply want to look at this figure. Let's consider the radius. First, the initial radius of the object while moving is r initial, and after some time that one it goes to r final. Obviously r final is the same as r initial, right? When the object is at r initial, it has an initial velocity, and when it becomes at r final, it is going to have a final velocity. Then if you look at the figure and see that delta v over v is equal to delta r over r, and that gives us the equation delta v equal v delta r over r. And if you divide both sides by delta t, the left hand side delta v by delta t is nothing more than the ar acceleration, while delta r over delta t is nothing more than the magnitude of the speed. So in this case we have v squared over r, and the acceleration is having this sign. Now the question, how did you get this relation that delta v over v equals delta r over? Now let's look at the figure again. Delta v, if we move this point from here, this vector v initial, and put it right parallel to it in here, this vector v initial parallel to this one, so it's the same vector. So we got now v initial in this direction and v final in this direction, as you can see. Now to get delta v, we get v final minus v initial, and this is the side of the triangle which is named as delta v. Again, delta v is v final minus v initial. Now we have two triangles, the red one and the green one. If you look at the v initial in here, v initial is perpendicular to r initial, and v final as tangent, and V final is perpendicular to R final also because it's the tangent to the circle. So, and R initial is the same as R final, it equals to R. And we have to notice that the angle between R initial and R final is the same as the angle between V initial and the final and V final. In this case, we can say that the red triangle is similar to the green triangle. That's why we can put delta V over V is equal to delta R over R, because the two triangles are similar to each other. And the triangles are similar, I mean this rule is applied, are similar. Why this rule is applied? Are similar when the corresponding angle are congruent and corresponding sides are all in the same proportion. And this is the case we have here. In here, as you can see, the velocity vector in this uniform motion is always perpendicular to the radius and is always perpendicular to the centripetal acceleration. As we said before, the change in the velocity vector causes the acceleration, and that acceleration is directed towards the center of the circle, as the minus sign indicated before. And we can write always a sub r equal minus v square over r, and again the minus sign is an indication that the direction of this acceleration is towards the center. We can find the time required for a complete revolution in this circle as well. If we know what is the complete revolution in rotating a one cycle, and this time is nothing more than the circumference of the circle 2 pi r divided by the speed v, which is constant. So as we said before, we have a relation between the time of one period or one revolution and the speed of the particle moving in a uniform circular motion. This example is relevant to this idea. We have here a wheel of a car with a radius of almost 0.3 meters and is caused to rotate of 830 revolutions per minute. Now you are asked to find the speed at which the outer edge of the wheel is moving, the outer edge in here, when it's moving in this velocity. Means you have to consider the radius from the center up to this point at the circumference. To solve this problem, we need to know that 830 revolutions per minute is the inverse of that, give us the time of revolution. And this time of revolution, which is 1.2 times 10 to minus 3 minutes, that is 0.072 seconds. This time of revolution is equal to 2 pi over 2 pi r, which is the circumference divided by the speed. If we want to get the speed, so obviously we just insert the radius of 0.29 meters and divide that by the time of one revolution. You're going to get the speed at the circumference, at the point on the circumference or the upper edge of the tire. The figure to the left and the one to the right are both examples for uniform circular motion. The figure to the left is a mass attached to the string, and this chap is rotating the ball horizontally. The only force that acts on the ball as centripetal force is the tension in the rope. And the tension in the rope is the only centripetal force that acts on it and keeps this ball moving with a constant speed and changing its direction. Now, the question you might ask, what about if this rope is cut? Well, if the rope is cut, in this case, the circular motion will diminish and the object will go in a straight line at the instant the rope is cut. Another example is the car moving on a circular path, on a circular track like this. When it reaches to the curved end here at this point, when the car becomes in here at the curved path, either it's going to continue its turn in the circle. This is part of the curve in here is part of the circle. You can make a full circuit out of it. Here you can make a full circle at this point here, like this. And at this point, the question you may ask, what centripetal force caused the car to keep into the track and moving in a circular motion? In a sense, it keeps its speed constant while it changes the direction from here right to there and continue in a circle. The answer is the static force of friction is responsible for this uniform motion. It is the only force that acts on the car to keep it in the track with a fixed radius, with a constant speed, and cause it to change its speed. That is the force of static friction. Well, the question, what about if this track in winter is icy? I mean, the friction is not there. What's going to happen to the car while it reaches this turn? Well, obviously, if the static of friction between the car and the road is gone, this means that the car is expected to go straight up like that. The same as the case for the tension when the rope is cut.